Welcome to this fourth session on sequential circuits. In this session, we will go through various types of flip-flops. All are derived versions of SR or RS flip-flop. Last time we considered first SR flip-flop, then SR flip-flop with enable input, then SR flip-flop with input giving complement of each other as D flip-flop, then we added a clock circuit block. So, till now we have considered four types: basic SR flip-flop, SR flip-flop with enable, SR flip-flop converted to D flip-flop, and clocked SR flip-flop. Now, in fact, this flip-flop is so rich module that we can even have 5-6 hours on various types of flip-flop, but for the want of time we cannot proceed. Therefore, we have to curtail to what is minimum required. So, based on this SR flip-flop, which is a cross coupled NOR gate, also you can have cross coupled NAND gate. We discussed SR flip-flop using cross coupled NOR gates. Similarly, we can construct SR flip-flop using cross coupled NAND gates, where only inputs are active low, that is the exact reverse truth table is there, but that we will discuss sometime, contains beyond syllabus, because once one type of flip-flop is known, rest we can develop very easily. Now, using this cross coupled NOR gate, that is SR flip-flop, we can go for various further combinations. Now, the flip-flop itself is having feedback. In that, we can add one more layer of feedback. Last time we had considered that the SR flip-flop is having like this. We can add some gates in which we have added enable input. Now we again use these AND gates, but we don't add enable input right now, but we use further feedback. So this one input we are having here, other input we are having here, and this input we connect it from the Q bar of the flip-flop, and this input we connect from Q of the flip-flop. It's quite interesting now. And then these are to be given now some names, that is Jack and King, like that names are given, maybe J and K, and then this is coming as Q and Q bar. This becomes very interesting circuit, and we can proceed with writing the truth table. What happens? It's very interesting. So, what we do is J and K we write here. Based on J and K, what would be S and R? We write here, and then we write what would be Q and Q bar. What would be? It's so we require 6 columns. It's, as I had already stated, it's very interesting, and we are, even though it's a first year course for non-domain students, we are explaining in enough details. Now we can have various combinations, simply 0 0, 0 1, 1 0, and 1 1. So very obviously there are two AND gates. So because of this feedback, what has happened? This Q bar has come here. This Q bar has come here. So this input is Q bar and this input is Q. This input is Q. So J and K are the inputs of the flip-flop. Inputs of this big circuit, which is now becoming a JK flip-flop, first version. Inside that we are having S and R flip-flop. This, depending upon S and R, we know how Q and Q bar are generated. So what we do, based on S and R, we know everything what is to be done. Now what is required to be discussed in this case is how J and K are making impact on S and R. Now, very simple. 0 is a decisive input for AND gate. So when J is 0, straight away S is 0. So wherever you find J is 0, you put S equal to 0. Wherever you find K equal to 0, you put R equal to 0. Put R equal to 0. So it is quite simple operation. Now, when J is equal to 1, what will happen? When J is equal to 1, straight away the output of the AND gate depends on other input. So when J is equal to 1, what I should write in case of S? When J is equal to 1, that time S would be Q bar. So can I write Q bar here? I write Q bar here. When J is equal to 1, I write Q bar as S. And when K is equal to 1, when K is equal to 1, the output depends on other input, which is Q. So here now basically there is feedback inside and there is one more layer of feedback, so it makes us a very interesting circuit. Now the purpose of this column is over. Purpose of this column is over because now we are knowing what is S, what is R, all four combinations, right? Here we don't know exactly, but we know it is Q. So based on Q, so we can work for Q equal to 0 and Q equal to 1. We can work for Q equal to 0 and Q equal to 1. So for each, now what is the situation? For SR, because of another layer of feedback, what I am getting this truth table to be completed, but in such a manner that other input is not known. Other input is output itself, just like the basic feedback circuit which we discussed at the first lecture. So we have to go for as what would be, now we mask it out and we have to separately discuss what would be output when S is 0 and R is Q. So if we want a very detailed explanation, instead of only working for this, we expand this. Expand this in the sense what? S and R, and we expand this in such a manner that S, R, Q, Q bar. So we have to write J equal to 0, K equal to 0 leads to S equal to 0 and R equal to Q, R equal to Q. So we should write what if Q is 0 and what if Q is 1? What if Q is 0 and what if Q is 1? So this first row we can write in the form of 0, 0 and 0, 1. I hope you have understood. Only thing is that I will change the colors. For this is constant, this is 0, R is 0 and R is 1. I hope the thing is very clear. I think I made a very small mistake here. What is the mistake? In just rush, when J was 0, S is 0, J is 0, S is 0. When R is 0, so when K is 0, what is the situation? R is 0. When K is 1, it is here. When K is 0, R is 0, and when K is 1, R is, what happens? R is Q. What I just missed out? J is 0, R sequentially, and K is 0, R is 0, K is 0, R is 0, K is 1, R is Q, K is 1, R is Q. I hope that it is just mistake because of J is 0, 0, 0 come sequentially here. Here 0 is there, 1 is there, 0 is there, 1 is there. So this is not there. So when this is only one common case, S equal to 0 and R equal to 0, no issue for the first case. I hope I once again clarify. When J is 0, S is 0, K is 0, R is 0. So J0, S0, J0, S0, K0, R0, K0, R0. J1, S is Q bar, J1, S is Q bar, J1, S is Q bar, K1, R is Q, K1, R is Q, K1, R is Q, right? So for S equal to 0 and R equal to 0, what will happen? Obviously, the flip-flop will maintain last state. Flip-flop will maintain last state because now we will find that in any case, both will not be 1. S equal to 1 and R equal to 1 will never occur in this case. As you see that here is S equal to 0, S equal to 0, R equal to 0, and here Q bar and Q bar and Q. So S equal to 1, R equal to 1 will never come. So as it never comes, I can comfortably write output as last state for S equal to 0 and R equal to 0. Now for the second case, so J equal to 0, K, see this now is for our internal calculation. After that it will go out, and only because this is not coming, it is internal S and R. So final truth table is J, K, Q, Q bar. So J0, K0, it is having S equal to 0, R equal to 0, Q bar is last state that I can comfortably write. Now for the second case, J equal to 0 and K equal to 1, J equal to 0 and K equal to 1, what I have to write? S equal to 0 and R equal to Q. R equal to Q means the current input R is not defined clearly, it depends upon current output Q. So if current output Q is 1, if current output Q is 1, or if current output Q is 0, then R will be 0, and if current output Q is 1, then R will be 1. If current, listen very carefully, it is a very fundamental discussion for JK flip-flop. When I have got J equal to 0 and K equal to 1, it leads to S equal to 0 and R equal to Q. What is Q? Current output. Now, if current output is 0, then R will be 0. If current output is 1, R will be 1. Now, for SR flip-flop, if S equal to 0 and R equal to 1, what it leads to? You might be recollecting, for SR flip-flop, the truth table is if S is 0 and R is 1, it gives me a fixed output Q equal to 0 and Q bar equal to 1. So here I can compute Q equal to 0 and Q bar equal to 1. Q equal to 0 and Q bar equal to 1. But now, if R is 0, what is the output? S equal to 0, R equal to 0, last state. But I will not write last state here. Why? Because why R was 0? This R is not 0 like here. Here R is always 0. Here R is Q. So R equal to 0 means what? Q equal to 0 and Q bar equal to 1. So what is the last state which I know? Here last state I don't know anything, any state can be last state. If S is 0 and R is 0, then last state I don't know because both are fixed zeros. In here I write last state, but here S is 0 and R is Q. So I have taken Q0 here and Q1 here. So if Q is 0, it becomes 0, 0. If Q is 1, it becomes 0, 1. If Q is 1, in that case means Q for J and K as 0, 1, Q and Q bar as 1, 0, because as Q is 1, Q bar is 0. So if J is 0 and K is 1, that time if Q was 1 and Q bar was 0, then the inputs S and R become 0, 1, that make outputs 0, 1 in any case. So j equal to 0, k equal to 1, q equal to 1, q bar equal to 0, result me into q equal to 0 and q bar equal to 1. Now, if s is 0, sorry, if j is 0, k is 0, then s becomes 0, r becomes q, and if q is 0, at that time q bar is 1. So, j equal to 0, k equal to 1, q equal to 0, q bar equal to 1 lead to s and r at 0, 0, and s and r at 0, 0 lead to last state, but last state is 0, 1 here. So, in any case it becomes 0, 1. So, I conclude if j equal to 0, k equal to 1 lead to s equal to 0, r equal to q. If q is 0, in that case SR becomes 0, 0 and last state of 0, 1 is continued. If q is 1, then s equal to 0, r equal to 1, new state is set as 0, 1. So, in any case j equal to 0, k equal to 1 result into such s and r where if last state was 0, last state of outputs was 0, 1, it is maintained, and if last state of outputs was 1, 0, it is inverted to 0, 1. So, irrespective of last state, output state is 0, 1. So, when j is 0 and k is 1, output state is 0, 1. Now, when j is 1 and k is 0, exact replica. So, here k is 0, j is 1, k is 0 lead to r equal to 0 and s equal to q bar. S equal to q bar. So, q bar can be 0, q bar can be 1. So, if q bar is 0, SR becomes 0, 0, last state is continued. What is last state? Q bar is 0 and q is 1 is last state. So, q bar is 0 and q is 1, this last state is continued. If j equal to 1, k equal to 0 lead to r equal to 0, s equal to q bar, and if q bar is 1, in that case SR become 1, 0 and SR equal to 1, 0 lead to outputs as 1, 0. So, if when j is equal to 1 and k is equal to 0, when j is equal to 1 and k is equal to 0, it results into s and r such that if last state is 1, 0, that state is continued, and if last state is 0, 1, if last state is 0, 1, that state is inverted to 1, 0. So, in any case the current output state is 1, 0. So, for j equal to 0, k equal to 0, last state is maintained, 0, 1, new state is 0, 1, 1, 0, new state is 0, 0, and now here it is most interesting. So, if j is 1 and k is 0, then what are s and r? If current state is 0, 1, if current state is 0, 1, if current q is 0, q bar is 1, then new outputs are 0 and 1, 0 and 1. If current state is q is 1 and q bar equal to 0, new outputs are, listen very carefully, it is the most interesting situation for JK flip-flop. J equal to 1 and k equal to 1, what that makes? Both inputs are direct outputs. If j is 1 and k is 1, SR flip-flop goes into such a state where its inputs are outputs only, just only thing is q connected to r and q bar connected to s. So, if q is 0 and q bar is 1, then if q is 0 and q bar is 1, new inputs are s equal to 1 and r equal to 0. If q is 1 and q bar is 0, new outputs are s equal to 0 and r equal to 1. So, what are the outputs here? 0, 1 and 1, 0 and 0, 1. What does it mean? It's very interesting situation. If q and q bar are if q, now we go for these two, it's most important thing. If q and q bar are here, if q is 0, q bar is 1, in that case output we obtain as 1, 0. If q is 1 and q bar is 0, output we obtain as 0, 1. What is this? This is exact reverse of last state. So, I can write last state complement. But what happens? It is just like an unending chain. It is an unending chain. Suppose if we decide, we have a simple logic, you do not hold the ball. If you have ball in right hand, you throw to left hand. If it is in left hand, you throw to right hand. Will ball remain stable? No. Why? Because no stable state. Ball coming in right hand, it means you have to throw it left hand. Ball coming in left hand, you have to throw it in right hand. So, it will be always dancing ball. Like that, what happens? If last state was 1 0, if last Q and Q bar, if last Q and Q bar were 0 1, new Q and Q bar become 1 0. But that new is again paid back. So, when they become, so Q bar 0 1 will decide to have Q bar as 1 0, and Q bar 1 0 will decide that they should become 0 1. Means just like a ball like this, or suppose if you have got two platforms and you throw the ball. If ball comes here, it rebounds here. If it hits here, it rebounds here. It is never ending. So, if J and K are 1 1, this is called as toggling. It is last state, it is toggling state, always toggling. Q bar 0 1, try to make Q bar 1 0. The moment they become 1 0, they try to make it 0 1. Again they try to make it 1 0. So, it will be always square wave at Q and Q bar. And what is the timing of the square wave? Depends upon how much time it takes for actually changing from 0 to 1. So, you will be getting square wave at Q and Q bar. If you keep J and K as 1 1, if you keep J and K as 1 1, you will get a square wave at Q and Q bar exactly complements. When Q is 1, Q bar becomes 0. After some time, Q becomes 0, Q bar becomes 1. This is a square wave. Now, if we decide to stop this square wave by, instead of using simple SR flip-flop, if we use SR flip-flop with an enable input. So, what is there in an enable input? So, that I will show you very easily. We can add it here also, but it is better that we add it here. So, what you have got? S, R, you have got one more AND gate here. So, this was what we have discussed, and this is E. This is E. This we can add, it is very interesting now. Now, when we add E, if E is 0, what will happen? If E is 0, irrespective of J and K, what is going to happen? If E is 0, whatever it might be, these two will be 0 0. When E is 0, irrespective of J and K, what is going to happen? S and R would be 0 0. So, last state will be continued. If E is 1, but these are 0 0 same. If E is 1, same. If E is 1, same. And if E is 1, again same thing, always toggling, right? Then you will ask me, why you added E? Are you making some fun of us? If we add E, then E equal to 0 results into last state, and when E is equal to 1, original truth table continues. But now, what I am going to do is, this E, I am not going to keep continuously 1. What I am going to have? I will have a switch. I will have a switch here, and what I will do, this E I think it is going beyond. I will just and for E, what I am doing, I am connecting a very interesting thing. It just was showing it is through a pull down, it is grounded and it is connected to plus 5 volt, that is logic high level, and a switch, plus 5 volt and a switch. This is my E output of this circuit. So, what will happen? Normally E will be low, normally E will be low. When I press the switch once, what I will do, it is a press switch, means not switch like this, just like a doorbell switch. I press and release. So, it would be 1 for very small time. So, when I press the switch, I will be giving a small pulse here. To this I will generate using clock later on. So, at E, I will be giving such small pulse. So, what will happen? When pulse at E comes, what will happen? The input J and K will be observed. Input J and K will not be observed when pulse is not there. So, input J and K will be just like suppose when teacher scolds, student give attention for some time and then again lose attention. So, the inputs J and K will be watched by my flip flop only when E is 1. So, at the time, very small time when E is 1, J and K are observed. If they are 0 0 last state, 0 1 0 1 1 0 1 0, and if 1 1, what will happen? It will complement to 1 0, again fade back, but complementing, again feeding back, and again moving ahead, time is required. And if my pulse is very small, in that case what will happen? Toggling will be there only for one time. If E is continuously 1, it will multiply toggle. If E is 1 always, or when E was not there, that time what is happening? That time it is happening like this. If Q is 0, 1, like this, and that time Q bar is exact complement. So, I get a square wave, and why this time? That is called a propagation delay of the gates, that is flip flop requires time to change. So, when J and K are 1 1, if this E was either not there or if E is 1 not continuously, then I get 0 1 1 0, again 0 1, again 1 0, means it continuously changes. But if I make E 1 for very small time, then what will happen? If I am making E 1 for very small time, J is 1, K is 1, if I make E 1 for small time, then that time it was 0 1, it will change to 1 0, and now as E has become 0, toggling will stop, because when E becomes 0, S becomes 0. Why toggling was occurring? Toggling was occurring because Q bar were coming in inverted mode. Q bar was coming here, means Q and Q bar are the effects of S and R, and they are fed back in, just like you might be knowing Lenz's law. It tries to oppose the cause producing it. S equal to 0 and S and R, 0 1 and 1 0, produce Q and Q bar as 0 and 1 and 1 0. This is flip flop, but they are fed back in such a manner that they try to kill themselves, means Q and Q bar are fed in reverse order, Q and Q bar. So, as it was here, toggling was taking place, but the moment at which E becomes 0, it is no longer Q bar, S and R becomes 0 0, because as E is 0, everything becomes 0 0. So, that time it will toggle only once. Now, but say if it is somewhat wide, then it may toggle twice. It may toggle twice. So, by having E, you can restrict once or twice, maybe thrice, but not when E was not there, it was continuously toggling. But when E is there, by putting a pulse at E, you can restrict toggling, but you can stop toggling. And when you restrict, if it toggles once, it is toggling. If it toggles twice, it is last state. If it toggles thrice, it is toggling. So, you do not know exactly how many times it has toggled. If it has toggled for odd times, it will be inversion, complement of last state. If it toggles for even times, it will be last state only. So, output becomes unpredictable because of the pulse width of E. How we do not know how many times the flip flop would toggle. Now, this small pulse, we are also discussed small pulse. Instead of connecting this, what you can connect here is the already known circuit which we have discussed last time, that is called as clock circuit block. You can connect inside a clock circuit. I will make the gates smaller in size, so I can get some space, and I can use a clock circuit block inside, and this is called as CLK. So, what this clock circuit block will do? Clock circuit block will give this out, this is E, your E. So, when E becomes 1, when there is a rising edge of the clock, at the time of rising edge of the clock, E becomes 1 only for 10 nanosecond period. So, E becomes 1 for 10 nanosecond period after rising edge. So, I can say this, instead of E, I can write this clock. So, if clock is 0, or if clock is 1, no use. If clock is down, no use. When clock is up, clock is up, clock is up, clock. At the time of rising edge of the clock, inputs are sampled and toggling takes place. But still problem is not solved because the clock circuit block will give me 10 nanosecond pulse. And then in 10 nanoseconds, when Z is, for these 3 cases, no problem. But for this case, when Z equal to 1, K equal to 1, and I give clock given makes this E1 for 10 nanosecond. So, for 10 nanosecond, toggling will continue. So, if propagation delay is say 7 nanosecond, then there will be only once toggling. If propagation delay is 4 nanosecond, then there will be twice toggling. If propagation delay is 3 nanosecond, it will be thrice toggling. So, there is a problem of multiple toggling, and how much times exactly depends upon propagation delay of the flip flop. So, it is unpredictable. So, if J is 1 and K is 1, multiple toggling takes place, and exact output, whether it will be last state or complement of last state, depends upon how many times toggling takes place, and it becomes unpredictable. Therefore, this is the problem of a single stage JK flip flop. It is a problem of single stage JK flip flop, and in order to avoid this, a master slave JK flip flop has been designed, and master slave JK flip flop is really a very wonderful circuit. It becomes the very basic building block of all digital circuits which contain counter, then maybe some kind of, or what happens is that JK flip flop becomes a universal flip flop which can either store the things, it can complement, and we can use counters, you can use shift registers, many what we can say basic circuitries which are required in your microprocessor, which is heart of a computer, are derived using JK flip flop. And whenever JK flip flop we refer, this JK flip flop is of no use. Why? Because when J is 1 and K is 1, and when clock is given, it will toggle, but toggle multiply. Multiple toggling is of no use. Therefore, whenever JK is there, we have to go for master slave JK flip flop, which we will draw now. So, it is very interesting, master slave JK. So, what is the problem? The problem here was when J was 1 and K was 1, outputs were connected back to inputs. Then when outputs are connected back to inputs, outputs are such that they change because of reverse feedback when J is 1 and K is 1. So, when J is 1 and K is 1, outputs will never become stable. They will always try to complement themselves, and we don't want that. We want that they should only complement once. How to ensure that they only complement once? That we want to ensure by any means. So now for that purpose, if it was a actual live lecture, then some time would have been given to you and we would have cross question, but that is not permissible. So we go for direct design. So we have S. We use two SR flip-flops. We use two SR flip-flops. Second SR flip-flop is very simple. And what we use clocked SR flip-flop. So what we mean by clocked SR flip-flop? Clocked SR flip-flop is active only for 10 nanosecond period after rising edge of the clock. Except that period, it is maintaining last state. So clocked SR flip-flop maintains last, when clock is 0, clock is 1 or clock is falling down. In all these three cases, since because of it is going through gates, irrespective of S and R, outputs are last state. Only S and for a clocked SR flip-flop, as we have seen in last lecture, the inputs S and R are checked only for a small period of 10 nanoseconds after rising edge of the clock. So both are clocked SR flip-flops. Outputs of master are fed to slave directly, and here is a reverse feedback. The feedback is not coming from master, but it is coming from slave. This is also clocked flip-flop. You might have found in some substandard literature, what do? They connect two independent ZK flip-flops in series and say that it is avoiding what we can say multiple toggling, which it doesn't. The feedback for master must come from slave, then only the purpose is achieved. And this is clock input. So it has got three inputs, J, K and CLK. So I hope that this arrow means a clock circuit block inside, and for this clock is also here, and it's in a very interesting manner it is connected. So same clock this is J, this is K, this is CLK. Is it observed? CLK is seen? Can I move somewhat left? It's right, okay. Then the same clock is connected to next flip-flop by inverting. So what will happen? When positive edge of this clock comes, it goes as positive edge for this flip-flop. So this flip-flop will be active for 10 nanosecond period after rising edge of the clock, and that goes as falling edge here, so it will not be active. So when there is a falling edge of the clock, this will not be active, but because of inverted to rising edge for here, so this will be active. So if I draw clock, then this clock is clock for this flip-flop, and for this flip-flop it will be inverted clock, means this falling edge will be rising edge for this. So the active time in which the first flip-flop will check its S and R is 10 nanosecond period from rising age. It will not check. So, in the period of it is master active, master JK flip flop active, or master, its overall is JK, we should, and these are final outputs. These we can say as master outputs, Q, QM and QM bar. This I can say QS and QS bar, but outputs are slave or outputs, so I keep it as Q and Q bar only. So Q bar means final outputs, QM bar means outputs of master. So this is the 10 nanosecond period after rising age of CLK is the period in which master is active, and the rising age is falling age for this, it is not active, but falling age is rising age for this flip flop. So for the 10 nanosecond period from falling age, the slave is active. So what happens? It's very interesting. At the time of rising age, master sets its output depending upon J and K. And at the time of falling age, slave follows master. Slave never looks at J and K. At the time of rising age, master decides the outputs depending upon J and K and Q bar. And what was the problem last time? Last time problem was Q and Q bar are fed back. Master, that time it was single flip flop. So Q and Q bar were fed back. That was making changes in S and R. That was again making changes in Q and Q bar. That was again making changes in S and R. But now what is happening? At the time of rising age, master will determine its outputs QM and QN bar depending upon old Q and Q bar. Right. So when J is 1 and K is 1 and rising age is there, if old Q is 1 and old Q bar is 0, QM will become 0. If old Q is 1 and Q bar is 0, QM will become 0 and QM bar will become 1, but that is not copied here. So a situation will never come where the outputs which are changed are traveling immediately. That never happens. So what happens? Rising age decides intermediate outputs. So the unending, what we can say, race never occurs. At the time of rising age, Q and Q bar of slave decide along with J and K, obviously. Listen very carefully again. At the time of rising age, Q and Q bar of slave or overall Q and Q bar, depending upon J and K as well, decide QM and QM bar. But it does not change Q and Q bar. So rising age decide master's output which are intermediate outputs. That time it does not change Q and Q bar. And then at the time of falling age, slave copies intermediate outputs. That time master is inactive. When slave is active, master is inactive. When master is active, slave is inactive. So an active master will decide intermediate outputs depending upon previous actual or final outputs. And at the time of falling age, the intermediate outputs decide final outputs. So I redraw everything again. I hope that it should be very well understood now. So watch very carefully now. So when CLK at the time of rising age, JK, that will decide S and, so what I do, CLK, JK, K, S master, S R master, Q master, Q bar master, S slave, R slave, Q and Q bar of slave, but I don't write it because Q and Q bar of slave are, is it seen till that? Okay. So there I will write Q and Q bar directly because slave outputs are actual outputs. So at the time of rising age, what happens? At the time of rising age, when clock is 0 or clock is 1, nothing happens. When clock is 0 and when clock is 0 and clock is 1, none of the things are active. So what we can write? We can write that also. Clock is 0, clock is 1, irrespective of this, irrespective of this, irrespective of this, it is last state, it is last state. No change occurs. Now, at the time of rising age of the clock, if J and K are 0, 0, if J and K are 0, 0, 0, 0 J and K result to 0, 0 S and R. 0, 0 S and R, it maintains last state, and irrespective of this, we are not bothered what these are, it maintains last state, because at the time of rising age, for the slave it is falling age. So no change. Then rising age, J0 K1, rising age, J1 K0. So J0 K1, J0 means this now I write as SM, RM, SS, RS. So J0 means SM0, K0 means RM0. Now K1 means what is RM? RM is Q, that is not QM, but RM is Q, and this is Q bar or QS and QS bar. So when J is 0 and K is 1, RM is Q, and when J is 1, K is 0, it is Q bar. Q means, always remember, it is slave or overall. It is overall Q or output of slave. Now this we discussed, that if slave was 0, if slave Q was 0, in that case it is 0, 0. That time, at the time of falling age, slave's outputs are set at the time of falling age. Means if we talk of this age, slave's output have been decided by this age which had followed master's output. So this Q means QM also. So this Q is last QM, but at the time of rising age, last QM is here but not directly, because when rising age occurs, it is output of slave which is current state of QM, but when it is going to change, it will not be coming back again. So if 0 and 0, in that case last state is maintained, and last state maintained is 0, 1 as we discussed last for single flip flop. If 0, 0 last state, if 0 and 1, then 0 and 1, S is 0, R is 0. This R is 0 means Q is 0, means last state was of Q was 0, last state of Q bar was 1. So if this S is 0 and Q was 0, then 0, 0 requires last state to be continued. But what last state? Last state was Q0 and Q bar 1. So that is continued. If S is 0 and Q is 1, that is R is 1. If Q is 1, in that case Q was 1, Q bar was 0. That results into S0, R1, and S0, R1 make outputs as 0, 1. So 0, 1 is the output for 0Q as the input, either because of continuation of last state or it exclusively makes it 0, 1. So either 0, 1 last state continues or 1, 0 last state is inverted, and exact reverse happens here. When R is 0, S is 0. S is 0 means Q bar is 0, means Q was 1. So last state was 1, 0, that is continued. If R is 0 and this Q bar is 1, means last state was 0, 1. But when this Q bar is 1, in that case current state is 1, 0. That 1, 0 will make this as 1, 0. So JK 0, 0 result into QM bar 0, 1. JK 0 result into QM and QM bar 0, 1. JK 1, 0 results QM and QM bar into 1, 0 irrespective of last state, either by continuation of the last state as it is or by inversion of the last state, but in any case new state has to be 0, 1 and 1, 0. Now if at a rising edge both are 1, 1, then what is the case? It is Q bar and Q. It is Q bar and Q. Now when it is Q bar and Q, what are the outputs? Outputs are exactly reverse. So if Q is 0 and Q bar is 1, it is 1, 0. So that is 1, 0. Q was 0, Q bar was 1. Now output becomes 1 and 0. If Q was 1 and Q bar was 0, input is 0, 1, output becomes 0, 1. So if previous state of actual output is 0, 1, new state of intermediate output is 1, 0. If previous state of output is 1, 0, new state of intermediate output is 0, 1. This is fundamental theme of JK flip-flop. So the actual previous output is inverted and remains as intermediate output. That doesn't appear on actual output again. So multiple toggling is completely avoided. So the master, when J is 0 and K is 0, master's outputs are old outputs of slave or old overall outputs. When J is 0, K is 1, master's output are 0, 1. When J is 1, K is 0, master's output are 1, 0. This all happens at rising edge. And at rising edge, if J is 1 and K is 0, then master's output are toggled version of slave's previous output or overall previous output, but not means those don't change again. So outputs QM and QM bar are Q bar and Q, or I can, if you want it to be specific, you can write is S and S, S and S. So, and this doesn't change, means outputs at the time of rising edge, if J is 1 and K is 1, then master's flip-flop S and R are Q bar and Q of slave's output, that make the outputs of master to change to Q, means intermediate QM of master is complement of QS of slave. Intermediate QM bar of master is QS. So it is master's output are slave's outputs complement, and that happens only once. The master's inputs, these are the, means what happens at the time of rising edge, these decide this, but this doesn't go ahead. So this doesn't change, this doesn't change. What I mean to say, since this active region or active timing and this active timing is completely disconnected, master's Q and master's input Q and Q bar of slave come as input of master at the this AND gate. So slave's output which are coming to master, they change intermediate outputs of master at rising edge, but at rising edge these changed outputs don't travel here. So when in the small window after rising edge, when master is active, these outputs are not changing, so toggling happens only once. And then at the time of falling edge, in any case, this is irrespective, this will maintain last state, and sorry, not this, irrespective of this will maintain last state. And now what are SS and RS? SS and RS are always, SS and RS are always what? QM and QM bar, QM and QM bar, that is these two outputs. So if this is Z at the time of falling edge, if Z and K are 0, 0, if Z and actually at the time of falling edge, at the time of falling edge, it doesn't check Z and K, it doesn't check S and R, it doesn't check this, only this is at the time of falling edge, it never looks at all these combinations. At the time of falling edge, the S and R of slave, S and R of slave are intermediate outputs of master which were decided during previous positive edge. So these are coming out at the output. So at the time of falling edge, these outputs come. So what happens when the J and K at the time of rising edge decide Q and Q bar of the flip flop at subsequent falling edge? Remember, J and K which are checked at this rising edge, so J and K are never sampled at falling edge. Only master samples J and K at rising edge, decides its output, and those are copied at this falling edge. So one rising edge, so this entire truth table, so this last state or this 0 1 or this 1 0 or this complement is simply copied at the output of the slave. So what a concise truth table of JK flip flop I can write as like this. I hope you understand it. It's too much exhaustive discussion. J, K, CLK. So a rising, we write like this, a rising edge and subsequent falling edge. A rising edge and subsequent falling edge, J and K at the time of rising edge decides overall Q and Q bar at this falling edge. This J and this K at this rising edge decide this Q and this Q bar at falling edge of this. So if J is 0, K is 0, it is last state. At the time of rising edge and at the time of rising edge, if these are 0, 1, outputs are 0, 1. At the time of rising edge, if these are 1, 0, outputs are 1, 0. And at the time of rising edge, if both are 1, 1, then at the time of next falling edge, so what happens? If J and K are 1, 1, at the time of rising edge, master toggles once. And at the falling edge, slave follows toggle master. So this is the crux. For I spend this much time so as to stress this thing, that at the time of rising edge, if J and K are 1, 1, then master toggles once, and at the falling edge, slave copies master. So we are sure that outputs are complement of last state. Outputs are complement of last state. So J equal to 0, K equal to 1, Q equal to 0, Q bar equal to 1, J equal to 1, K equal to 0, Q equal to 0, Q bar equal to 1. So this sets the flip flop, this resets the flip flop. This is Q is considered as 1 means set and Q0 means called as reset. So J0, J1, K0 sets the flip flop, J0, K1 resets the flip flop. So J is called as set input, K is called as reset input if other is the active. So J0, K1 flip flop reset, J1, K0 flip flop set, J0, K0 flip flop is neither reset not set, means it is continued what it was, and J1, K1 flip flop toggles. J0, K0 flip flop continues, J0, K1 flip flop resets, J1 K0 flip flop sets, J1 K1 flip flop toggles. This is called as JK master slave flip flop, and the final diagram of master slave flip flop which you will always require when we design counters. This is called as JK flip flop, JK Q bar, and it is shown like a bubble CLK. Why? Because outputs change at falling edge. JK master slave flip flop is double triggered, means at the rising edge master's inputs are master sets at the time of rising edge, depending upon inputs master's outputs are set, and at the time of falling edge the slave follows master, but final outputs appear only at the time of falling edge. Therefore, a bubble is shown indicating that the final outputs appear at the time of falling edge. So, the truth table is as stated JK only, and clock actually to be precise it should be like this and like this, but this is normally not drawn. We say that at the time of falling edge J0 K0 Q bar last state at the time of falling edge, at the time of falling edge, at the time of falling edge 0 1 flip flop reset, 1 0 flip flop set, 1 1 flip flop toggled. So, last state complement. So, if Q was 0 means if Q was 0 Q bar was 1, it continues 0 and 1, and in this case if Q was 0 Q bar was 1, it becomes 1 and 0, it toggles only once. This is master slave JK flip flop, and this master slave JK flip flop is the building block for designing counters. So, I hope that in the next session we will go for counters. It is enough for this session, it was exhaustive session.